All right. Okay, so it's a pleasure to introduce Harold Blum, who will talk about an algebraic version of the Hamilton-Tian conjecture. Go ahead.
Thank you for the introduction, and I'd like to thank the organizers for organizing this event. It's a pleasure to speak. So what I'll be talking about today is all going to be joint work with Yuchen Liu, Chenyang Xu, and Ziquan Zhuang. And throughout the talk, I'm going to be working over the complex numbers. So what I'll be talking about is something that's very much motivated by complex geometry, but it, again, similar to what we've heard in some of the lecture series, it will be purely algebraic. So first, let me just start off with the motivation that's coming from Kahler-Einstein metrics and K-stability. So for now, I'm just going to have X be a smooth Fano variety, meaning X is projective, smooth, and minus Kx is ample. And I'll be in this setting because some of the complex geometry results I'll cite in the next slide are only known in that setting. 1 second. Okay. So let me just recall some of the basic things that we saw in some of the lecture series on K-stability. So in complex geometry, a natural way to study our Fano variety X is to look for a Kahler-Einstein metric on the Fano variety, which is just some Kahler metric that satisfies some essentially differential equation where this omega is in the class of the first term class of X. So the key features of this theory, the first key feature is that this Kahler-Einstein metric is essentially going to be unique. It's going to be unique up to acting on it by the identity component of the automorphism group, which is a classical theorem of Bando and Mabuchi. A second important feature of the theory is this YTD conjecture, which says that X is K polystable, which is some algebraic criterion, is equivalent to the existence of a Kahler-Einstein metric. Sorry, I'm having trouble with my iPad. Kahler-Einstein metric on X, and the related algebraic criterion is K semi-stability, which can be characterized in terms of saying that it degenerates to something that's K polystable, or X degenerates to a Kahler-Einstein Fano. So in the first case, this is, in the smooth case, this is a celebrated result of Chen, Donaldson, Sun, and Tian. And the second part is an extension due to Qi Li. And then the last key part of this theory that we saw is that from an algebraic standpoint, the key application of this theory is that if we look at families of K-semi or K-polystable Fano varieties, then these objects have a nice moduli theory. Okay, so now with these key points in hand, I just want to bring up the following issue that we'll address today. And the issue is some trivial statement. So it's the fact that these above statements give us tools for understanding K semi-stable or K polystable Fano varieties. But of course, we know that many Fanos are not K semi or K polystable. So in dimension 2, the examples of smooth objects that satisfy or that are not K semi-stable are just going to be 2 small examples, P2 blown up at 1 point or 2 points. But in higher dimensions, there are obviously much more examples. And then if we look at singular Fano varieties that are KLT, you get many more as well. So the natural question that comes up is, what can one say using the K-stability theory about K-unstable Fano varieties? So from the complex differential standpoint, there's a natural thing that we should do. So instead of looking at Kahler-Einstein metrics, there's a larger class of canonical metrics to look at. And what these are called Kahler-Ricci soliton. So again, these are going to correspond to some Kahler class in the first Chern class of X, but then there's going to be some extra data. So there's going to be the data of a holomorphic vector field, and where this is going to be coming from is the action of some torus acting on my Fano variety. And then I take some weight vector, xi, in the co-weight vector space. Okay, so now with this data, what a Kahler-Ricci soliton is something that satisfies the Kahler-Einstein equation, but then you add some extra term, and this extra term is going to be the Lie derivative along this holomorphic vector field of my 1-1 form. So the key things about these types of metrics, well, the first thing is similar to above. These are going to be unique up to automorphism again, and this is a result of Tian and Xu. And I want to mention that when I say this is unique, I also mean that essentially the choice of this vector field is also unique. So there's a natural choice for the vector field. And in computations, it's often easy to see what the correct vector field is. The second thing about this theory is that, again, we have some algebraic criterion. And there's some notion of K-stability. So this pair of X with the vector field is going to emit a Kahler-Ricci soliton. If and only if this satisfies some condition, which is also called K polystability. And this can be defined similar to how K-stability was defined in the lecture notes. So you can define it using test configurations and look at a version of the Futaki invariant, but here you kind of modify it using the vector field. And also you have some valuative criterion in terms of some twisted version of the delta invariant using the vector field. But I won't define things until a little bit later in the talk. So this equivalence is due to Datar and Sekalidi as an extension of the results on the previous page. And maybe since some people are probably not familiar with this, let me just put some examples down. So some examples of things that emit Kahler-Ricci solitons. Well, it turns out that all smooth Fano varieties in dimension 2 are going to emit Kahler-Ricci soliton. And there's some natural, so essentially those two cases that weren't K semi-stable, the blow up of P2 at a point and 2 points, there's some natural vector field that you can choose in those two cases. And maybe another example is all torque varieties are going to emit such metrics, or all Fano torque varieties, of course. Okay, but something I should point out is still not every Fano variety is going to emit Kahler-Ricci soliton. So in dimension 2, there are singular KLT Fano varieties that don't emit Kahler-Ricci soliton, And in dimension 3, you can actually find a smooth example where there is no such metric.
So Harold, can I ask a stupid question? So for toric varieties, is it possible to say what the vector field is?
So I'll kind of mention this a little bit, but there's some function on, so there's some function on the co-weight vector space, and it's going to be correspond to the minimizer of that function. In this silly example of the blowup of P2 at a point, it's going to be some vector field that essentially fixes the -1 curve, essentially.
Thanks.
Okay, so a natural question is, how does one, from the complex geometric standpoint, construct these metrics? So the way one does this, or one of the ways to do this, is in terms of the Kahler-Ricci flow. So we start with some Kähler metric, omega naught, in the first trig class, and then you can apply the Kahler-Ricci flow, which is essentially some partial differential equation. And then the Hamilton-Tian conjecture, what this statement says, which is actually a theorem due to Chenyang Xu, and later a different proof was given by Bandler, says that if we take a Fano variety X and we take some metric omega naught, then I can look at deforming the metric along the Kahler-Ricci flow. And as t goes to infinity, if I take the Gromov-Hausdorff limit of the corresponding metric spaces, then you get some object y and some metric omega y. And y is going to be a KLT Fano variety. And omega y is going to be a Kahler-Ricci soliton. So the key point of this from the algebraic standpoint is what this is telling us is that any Fano variety, smooth Fano variety, degenerates to one that emits a Kahler-Ricci soliton. So what I mean by this is that you could find some family over a curve such that or some family of Fano varieties over a curve such that the generic fiber is just isomorphic to our original Fano variety X, and then the special fiber is going to be this variety Y that shows up in the above theorem. So what we'd like to do is try to understand this process from a more algebraic standpoint. So in doing this, let me first talk about the work of Chen, Sun, and Wang, which reinterpret this degeneration as happening in two steps, essentially. So they noticed that there's some construction where we take the Fano variety X, and then we can look at this object that I'll define called an R degeneration, which is a degeneration that also gives a vector field. So we get some Fano variety X naught and some vector field. And then there's some second natural degeneration to some new Fano variety Y. and some second vector field such that this admits a Kahler-Ricci soliton. So they observed this construction, and they also asked, or I guess they conjectured, that there should be some algebraic way to understand this. So this question of trying to find such an algebraic formulation was answered, or was first answered in the work of Dervin and Zekalidi, and then built on in the work further in the work of Han and Li more recently. And it describes what these two degenerations are. So this first degeneration, as I said, is what's known as an R degeneration, which is an object that's more general than just a degeneration coming from a test configuration. And it's going to be corresponding to some degeneration that minimizes some functional, which I'll define soon. And the key feature is that this special fiber that we degenerate to is going to be K semi-stable. And then the second degeneration is going to be a test configuration. So recall, this means that we have some GM equivariant family over A1 where this degeneration occurs. And then the special fiber of this degeneration Y is going to be K polystable. So let me just make some remark about what this construction looks like in two simple examples. So in the first simple example, where let's say X is K semi-stable, then this first degeneration is going to be trivial. So X is going to be the same thing as X0. And this vector field is going to be trivial as well. So nothing really, or I guess, at least this first degeneration isn't very interesting there. Maybe a second example, which is also going to be quite simple, is when X is toric, then X is the same thing as X0, but this R degeneration isn't necessarily going to be trivial, meaning that it gives some extra vector field. But maybe the most interesting case to consider is if you take a Fano variety that's K unstable and has no vector fields, then this first degeneration has to be non-trivial, and the complex structure is going to jump. Any questions? So let me just talk about some related constructions to emphasize that this is somehow very natural. So the first construction, I think it was partially inspired this two-step degeneration process. So the first construction is a local version of this, where you start with a KLT singularity. And then it turns out that this always admits a, I guess, partially conjectural two-step degeneration. And this two-step degeneration is using this normalized volume function. And this was motivated by analytic work of Donaldson and Son. And then there was an algebraic framework given for this using this normalized volume function due to Li, and then work of Li Shu and Li Wang and Xu. And I think Chenyang will be talking more about this on Friday. So let me also mention a much more classical two-step degeneration process. So let's say E is a vector bundle on a smooth projective curve. Then the point is this vector bundle E admits a Harder-Narasimhan filtration. And using the Riesz construction, this gives me a degeneration to the associated graded of the Harder-Narasimhan filtration, which is going to be a sum of semi-stable vector bundles. And then if I take this direct sum of semi-stable vector bundles, I can look at the Jordan-Holder filtration for each of those semi-stable vector bundles and degenerate to the associated graded of that. So each degenerates to a sum of stable vector bundles. So we can think about this as some analog of the Harder-Narasimhan and Jordan-Holder filtration in this setting of K-stability. Okay, so let me talk about the main results. So the main results is about trying to understand this from an algebraic standpoint. And the point is that a lot of this previous work about this two-step degeneration process really only works for smooth Fano varieties, since that's the setting where results from Kahler-Ricci flow can be applied. So the main result I want to talk about today is joint work with Liu, Xu, and Zhang. And this is also going to very much build on work of Han and Li. So what it says is for any KLT Fano variety, there always exists a two-step degeneration as I mentioned above. Where this first degeneration gives us some object with a vector field, and then the second is going to be coming from some test configuration. And the key features is that this first degeneration is K semi-stable, and the second one is going to be K polystable. And furthermore, if I look at this two-step degeneration process, both are going to be uniquely determined. And another new statement is that this second degeneration, the end product in this case when our original Fano variety was smooth, we knew that this admits a Kahler-Ricci soliton because it's essentially coming from this Kahler-Ricci flow, but it turns out it's also new that this, or in the singular case, that this admits a Kahler-Ricci soliton. Okay, so let me just mention that this proof of the second part uses some extension of what we heard about in some of the lecture series. So we know that this second object is going to be K polystable for K stability with respect to this vector field. And this implies some stronger notion by some slight extension of the work of the work that we heard in the lecture series. And then the work of Han and Li shows that this admits a Kahler-Ricci soliton. So already on the complex geometric side, this tells us something new, that we can always degenerate a Fano variety, a KLT Fano variety, to something admitting a Kahler-Ricci soliton. But what I want to talk about for the rest of the talk is trying to understand this problem from the algebraic framework. And then if I have time at the end, talk about what this says about trying to understand moduli theory for K-unstable Fano varieties. So what I'll really be talking about for most of the talk is trying to explain where this first degeneration is coming from, since this is the most interesting one when understanding the unstable objects. Okay, so to understand this first degeneration, where it's really coming from is looking at R degenerations, and these R degenerations are coming from things that we've seen about, that we've talked about relating to valuations. So let me just recall some notation and constructions. So I can look at the space of valuations on my Fano variety X. So here I'm going to be looking at valuations that are real valued and trivial on my base field, the complex numbers. So the key examples of such valuations, we saw some of these in earlier talks. The first are going to be divisorial valuations. So here we have some proper birational morphism, y to x, and then y is going to be smooth. And then we take some prime divisor E on y, and we can look at the valuation that comes from taking a function on x and then pulling it back to y and seeing how it vanishes along E. So in the lecture notes, or in the lectures on K stability, these were somehow the most important valuations. And it turns out in this talk, we also really care about quasi-monomial valuations. So here, let's just recall, it comes from a similar construction, but what we do is we take some not necessarily closed point on y, and then we look at some local coordinates at that point, and we choose some weight vector and then using these weights, we can cook up some valuation where this valuation, essentially, it's defined by first saying what it is on these local coordinates, and then extending to monomials, and then essentially you're going to make it the minimal valuation that takes those values. Okay. So with this construction, then I can say what these R degenerations are coming from. So these R degenerations are going to be coming from looking at the section ring of my Fano variety. So I'm going to be looking at the anti-canonical ring. And then, as we've done before, for evaluation, we can look at the associated filtration of the section ring. So the way this is defined is we take the lambda part of this filtration as just the sections in my section ring that take value at least lambda. Okay, and the point is that using this filtration, we can look at the associated graded. So recall the way this was defined. Is I look at the part of this filtration where I have sections that vanish to least order lambda, and then I mod out by sections that vanish to order strictly greater than lambda. And if you think about how this is graded, essentially this part is going to be 0 unless lambda lies in a fixed set of values. So essentially lambda should be one of the values that this valuation takes on the function field for this not to be 0. Okay, and then, whoops. Sorry, my iPad screen is really giving me problems. Okay. So then, like, important case is that when this associated graded ring is finitely generated, then we get some degeneration. So we get some degeneration from x to x0, and this is just going to be the proj of this associated graded ring. But there's some additional information. So the point is there's some additional data that's coming from this grading by gamma. So this grading by gamma is going to induce some torus action on x0. And then also, essentially, the values that gamma take is going to give me some co-weight vector. So there are different ways to think about what this degeneration is. So one way to do this is, so in the simplest case, when V is just a divisorial valuation and it takes Z values, this degeneration can really just be realized as some test configuration, and X0 is going to be the special fiber of the test configuration. But more generally, if V is just maybe some quasi-monomial valuation, there's a way to formulate this degeneration as some family over some affine family of Fano varieties over some affine toric variety. And then X0 is the Fano variety over the special closed, or the point that's a single orbit. Okay, so now that I've told you about these degenerations, we can look at this special functional that is going to pick out a canonical such R degeneration. So this H functional is partially inspired by certain functionals in complex geometry and algebraically formulated in this way in the work of Han and Li, building on also work of Dervin and Zekalidi. So this is going to be some function from the valuation space to the real numbers union plus infinity. And it's going to be related to certain functionals we've seen before. So the first term is going to be the log discrepancy. And then the second term, it's not quite going to be the S functional that we saw previously in the lecture series. It's going to be this S tilde functional. So as I mentioned, this first term, the log discrepancy, for valuations, this was defined in the work of Johnson and Mustatsa, and in more generality, in the work of Buxom, Defernay, Favre, and Urbanati. But in the simplest case, when you have something divisorial, this is just going to be the normal log discrepancy in birational geometry. And then the S tilde functional is going to be some nonlinear version of this S functional that we've seen in some of the lecture series. So let me just define it when we have a divisorial valuation. So it's going to look a little bit weird. And I think it really, maybe it's natural that it has some exponential function showing up because this is somehow coming from Kahler-Ricci flow. And I think some of the computations you do in that setting, this comes about. But the way this is defined, or one way to define this, as minus log of 1 minus this integral. So this integral is going to be a variant of one that we've seen before, but we have this exponential showing up. Okay, and one thing to note is, I guess, if you think about what this function is, you can think about what this integral is, and it's essentially going to be some value between 0 and 1. Hence, this logarithm is going to be well defined. So one key remark about this function, so I only defined it for divisorial valuations, but I want to emphasize that this log discrepancy function is a linear function, or is homogeneous, but that's not going to be true for this S tilde functional. So in general, when you scale your valuation, you're not scaling the function. So this makes the function have quite different behavior than what we've seen in some of the lecture series. Okay,
Wait,
so
Harold, can I ask something? So is it very complicated to say what it is for C terms, this divisorial valuation?
like I think I think it's very much dependent on what this function looks like. So maybe one interesting thing that I can point out. So you can take some valuation, V, and I can scale it by T, and I can look at the derivative of this at T equals 0. And it turns out that the derivative of this function at T equals 0 is just going to be, or no, I guess this will say what the answer was. So if I look at the derivative of this function, then it's going to be equal to just the original A minus the normal S functional, or Fujita's beta invariant. So this is related to what we're going to see on the next slide. The point is that as I vary this value T, I get something that's going to be convex, and the derivative at 0 is going to correspond to the original Fujita's beta invariant.
Thanks.
Okay, so now we can consider the following minimization problem. So I'm going to call little h of x the infimum of this h functional. So I'm taking the infimum on the entire valuation space and including looking at the trivial valuation. And the first thing that you can show about this functional was observed by Han and Li. And it says that x being k semi-stable is equivalent to this function being non-zero, or sorry, being non-negative. And then this latter statement is equivalent because you can just look at what happens at the trivial valuation. At the trivial valuation, the log discrepancy is going to be 0. And I guess I didn't define it, but the S tilde function is also going to be 0. So this is equivalent to saying that this invariant is 0 and computed by the trivial valuation. So now a natural thing to do is when x is not k semi-stable, we can study the minimizer. So before I begin talking about this, maybe I'll mention one other interesting class of valuations that are going to be the minimizer. So in the case when you have your Fano variety X and some vector field, that vector field is going to induce some valuation, and that valuation is going to be the minimizer if and only if X comma the vector field is k semi-stable. So essentially generalizing this case stated above. But more generally, you could have an arbitrary or a more complicated valuation computing the minimizer. So there have been a number of works understanding what happens. So the first statement that was proved is that there exists some quasi-monomial minimizer. So this was shown in the work of Han and Li. And the proof of this kind of mirrors some of the statements that we've seen before for the delta invariant and other minimizers that show up in k-stability. So the next statement is that that minimizer is actually a unique valuation. So it's not just unique up to scaling, but a unique valuation in the valuation space. So this was first shown by Han and Li under an additional assumption that the associated graded was finitely generated. And then the latter condition was verified, and we also gave a different proof of this uniqueness without using finite generation. And then the last statement is building on the work in the lecture series on the finite generation theorem for valuations. We show that the associated graded ring of this is going to be finitely generated as well. Okay, so as a consequence of these 3 points, we get our first step in the degeneration process, some R degeneration, and then some vector field on that variety. Okay, any questions up to this point?
So I'm sorry, so can I ask something?
Yeah.
So I'm not sure that I understood where the vector field came from.
So essentially, I guess there are 2 different ways to think about it. So the point is that this associated graded ring, it has some grading induced by, there's some grading gamma that I mentioned, and this is coming from the value group of the valuation. So the point is that this value group, it's some semi-group, and you can write it as some subgroup of z to the r, essentially. And this is coming, you can think about this as coming from the weights that you're putting on the quasi-monomial when you make the quasi-monomial valuation. So that's essentially giving you the torus action. And then you can also use that construction to get you the co-weight vector.
Okay, thank you.
So maybe the more canonical way to think about it is if I didn't say how to do this, but you can take this degeneration using some Riesz construction and some degeneration on some affine toric variety. So essentially that affine toric variety is giving you the torus action. Okay. So maybe I don't have time to talk about all the things that go into this theorem, but maybe I'll quickly talk about the uniqueness, since we've heard a lot about finite generation in the lecture series. So to prove the uniqueness, you want to naturally assume that these valuations both compute are infimum. And then the natural thing to do is to try to construct some path connecting those valuations. So instead of constructing a path connecting those valuations, what you can do is you can construct a path of filtrations interpolating between the filtrations induced by those 2 valuations. So the way this is defined is I can define the teeth filtration and the lambda part of that filtration as just the span of sections that vanish to the proper order along the 2 valuations. Okay, so now that I've constructed this path, my claim is that I can look at this H functional along this path. So to do this, I need to define what it means to take the H functional of the filtration and not just of evaluation. But you can do this using essentially log canonical thresholds rather than the log discrepancy function. And then you still use some analog of the S tilde function. So then the claim you want to show is that if these valuations aren't the same, then if I look at this function along the path, or I look at the value of this H functional of the filtration, then this is going to be strictly convex. And since this is strictly convex, you get that you can't have both minimizers at 0 and 1. So let me just also note that this argument kind of mirrors, in a way, an argument or a related argument for the normalized volume function observed by Chenyang and Ziquan as well. Okay, so in the remaining amount of time, let me talk about why this construction is interesting from the moduli theory, the moduli standpoint. So let me just recall.
I'm sorry, can I ask something about this? So, but the intermediate steps are also valuations or not?
Sorry, I'm having trouble with my. Yeah, so the immediate steps, they're not, in general, they're not always going to be valuations. If you just take two, so those filtrations along the path will not always be.
So if you know that the endpoints are minimizers, I mean, how do you have any control about the ones in between? I mean, if they're not part of the set you considered before?
Yeah, so you're right. So I'm glossing over a lot here, but the point is you can extend this H functional to filtrations, and then infimum of H on the space of filtrations is going to be the infimum of the H on the space of valuations.
Okay, thanks.
So I'm definitely glossing over things.
Okay, I also had a question. So this strict convexity statement.
Yeah,
that's not this. You're not assuming that V0 and V1 are minimizer here. I mean, it's more general, isn't it?
Yeah, so I think you're right. That's going to be more general.
Okay, thanks.
Okay. So maybe I'll, in the last bit of the talk about applications of this to moduli theory. And part of this is some, what I'll talk about at the end is a little bit conjectural. So let me just recall what we talked about in some of the lecture series. So we can look at the entire stack, the moduli stack, which I denote here as M Fano, which is going to be the moduli stack parameterizing KLT Fano varieties of dimension n and volume V. So if we want some nice moduli theory, one thing we can do is look at this substack of the K semi-stable Fano varieties. And due to a lot of work and recently finished in the work of Li, Xu, and Zhang, we know that this the stack of K semi-stable Fano varieties is going to be a finite type Artin stack, and it admits a projective good moduli space parameterizing the K polystable Fano varieties. So the natural question is, what can we do about the locus of unstable Fano varieties? So one thing that we can do is we can think about, instead of Fano varieties, we can think about Fano varieties with a vector field. So the expectation is that there exists a proper moduli space. Parameterizing K polystable pairs.
Hi, Harold.
X
I think
with
you
a,
missed the Patafavi in the theorem.
oh, I meant to have him. I included his co-author.
And maybe also Daniel.
Yes,
There are so many people, so easy to forget.
yes. Unfortunately, this is being recorded, so I'll apologize to them after. Okay. So where was I? Okay, so the expectation is that we should have some proper moduli space parameterizing pairs X with some vector field. And part of this expectation is actually known. So in the smoothable case, the properness is going to follow from some work of Fang, Sturm, or Fang, Song, and Sturm. Which extends work of Donaldson and Son when there's no vector field. And as well, there are some results on the construction of such a moduli space. Using analytic results of Fano. So one thing that's natural that we can do if we want to take advantage of this theory is we can look at some stub stack of all Fano varieties, KLT Fano varieties. And I can look at this substack that parameterizes those where this H invariant is greater than C. So one thing that we can say about this substack is that this is going to be a finite type Arden stack. And the next part is going to be a somewhat more conjectural picture, or conjectural at this point. So the idea is that we want to understand the two-step degeneration process from a moduli theoretic standpoint. So what I can do, or what we hope we can do, is we can look at this substack, which it turns out is going to be some open substack, and then we hope that there should be some closed embedding from this into the substack of K semi-stable pairs with this H value equal to C, where I'm looking at pairs X with a vector field. And then we can look at the next step in the degeneration process, and this closed, or I guess this stack over here is going to emit some proper good moduli space. So this will parameterize the polystable objects. Okay, so I know I'm going a little bit over, so I'll end the talk there and happy to answer any questions. Thank you for listening.
All right, let's thank Harold. Any questions?
Yeah, I have a question. So if you have an arbitrary family of Fano varieties, then this construction gives a map to the moduli of these Fano varieties with Kahler-Einstein metric. And what can you tell me about this map?
Or like, yeah, I'm not sure exactly what we can say right now, but I guess you get some locally closed decomposition of the base, and then I guess those subsets are going to map to certain strata is the point.
And so you think this map is constructible, or?
Yeah, I'd say this is likely constructible.
Mm-hmm. Okay.
Maybe my co-authors have other opinions.
I think it might be locally something like some sort of like a non-reductive GIT picture. I mean the map from the stack to the K semi-stable stack. I mean the general Fano variety to the stack of Fano variety with the Boros action and the K semi-stable action condition. I think this map might be some sort of non-reductive GIT.
Other questions or comments? If not, let's thank Harold again. And I think now it's time for social hour.